Scene script. Have you ever wondered what lies at the very center of our planet? Imagine plunging down through layers of rock, soil, and mantle, enduring escalating temperatures and pressures until you reach the Earth's core. Here, beneath thousands of miles of crust and mantle, you'll find the planet's beating heart. Now, what does this heart look like? Well, it's not a fiery inferno or an underground ocean as some folklore might have you believe. Instead, it's a solid sphere, primarily composed of two metallic elements, iron and nickel. That's right, the Earth's core is a gigantic, solid ball of these metals. You might be thinking, but isn't iron supposed to melt under such intense heat? Under normal circumstances, you'd be correct. However, at the Earth's core, the conditions are anything but normal. The pressure is so immense that it keeps these metals in a solid state, despite the scorching temperatures that far exceed those on the surface of the sun. Speaking of temperatures, let's take a moment to consider just how hot it is at our planet's core. The outer layers of the Earth shield us from the core's extreme heat, but if we could somehow withstand the journey to the center, we'd encounter temperatures that reach up to 9,000 degrees Fahrenheit. That's hotter than the surface of the sun. But the Earth's core isn't just a static ball of metal, it's dynamic and constantly in motion. This movement generates our planet's magnetic field, which protects us from harmful solar radiation, and plays a crucial role in many geological processes. So, at the heart of our planet lies a solid ball of iron and nickel, enduring immense pressure and extreme temperatures. It's a place of extremes, a testament to the incredible forces that shape our planet, and a reminder of just how dynamic and complex the Earth truly is. Just outside the solid inner core there's another layer, but this one is different. It's a roiling sea of liquid metal, known as the outer core. This layer, which extends roughly 2,200 kilometers, is in a constant state of flux, heated by the intense pressure from the layers above, and the heat radiating from the inner core. The outer core is primarily composed of iron and nickel, similar to the inner core, but in a molten state. This liquid layer swirls and churns around the inner core, driven by the heat and pressure from the layers above and below. Now here's where it gets interesting. This swirling fluid outer core is responsible for generating Earth's magnetic field. It's a bit like a giant dynamo, with the molten iron and nickel creating electrical currents as they move, which in turn generate the magnetic field that protects our planet. The outer core, a sea of molten iron and nickel, plays a crucial role in creating our planet's magnetic field. But how did these layers come to be in the first place? The formation of Earth's core is a story that begins over 4.5 billion years ago, with the birth of our solar system. Amidst the cosmic dust and gas, particles began to collide and stick together in a process known as accretion. Over time, these tiny particles formed larger and larger clumps, eventually giving rise to planetesimals, the building blocks of planets. Among these planetesimals was the one that would become our Earth. As it grew larger, the heat generated from the impacts and from the decay of radioactive elements caused it to melt, setting the stage for a process called differentiation. Differentiation is a process as natural as oil separating from water. In a molten world, heavy elements like iron and nickel sank towards the center, while lighter elements like silicon, oxygen, and aluminum floated towards the surface. This movement of elements resulted in the formation of distinct layers, with the densest materials forming the core, and the less dense materials forming the mantle and crust. But the story doesn't end there. The sinking of heavy elements towards the center released gravitational potential energy as heat, causing the core to remain molten. This molten outer core, churning and flowing, is responsible for generating Earth's magnetic field, a protective shield that guards us from harmful solar radiation. Meanwhile, the lighter elements that floated to the surface cooled and solidified, forming the Earth's crust, the thin, rocky shell on which we live today. So, from a cloud of cosmic dust and gas, through processes like accretion and differentiation, our planet took shape. The heavy elements sank to form the core, the heart of our planet, while the lighter elements rose to form the mantle and the crust, the skin of our world. Through processes like accretion and differentiation, the Earth's core took shape, forming the heart of our planet. Did you know that without the Earth's core we wouldn't have a magnetic field? Now that's an interesting thought, isn't it? Let's delve into what's known as the geodynamo theory to understand this better. This theory suggests that our planet's magnetic field is generated by the movement of iron within the Earth's molten outer core. Imagine billions of tons of iron and nickel swirling and sloshing around, driven by the Earth's rotation and the heat escaping from the inner core. This creates electric currents which in turn generate the magnetic field. It's a fascinating and complex process happening right beneath our feet. And why is this magnetic field so crucial? It acts as a protective shield, deflecting harmful solar radiation and charged particles that constantly bombard our planet. Without this invisible barrier, life as we know it would be impossible. The movements within the Earth's outer core create a protective magnetic shield around our planet. Now, let's consider the boundary between the core and the mantle. This invisible line, known as the core-mantle boundary or the transition zone, is more than just a geographical marker. It's a dynamic interface where two of Earth's major layers interact, each with its distinct properties and behaviors. The core, composed mainly of iron and nickel, is a world of extremes. It's incredibly hot, with temperatures rivaling those on the surface of the sun, and it's under immense pressure. On the other side of the boundary we have the mantle, a thick layer of semi-solid rock that wraps around the core like a protective shell. So what happens at this boundary? The answer lies in the phenomena of mantle convection and plate tectonics. Mantle convection is the slow churning motion within the mantle caused by heat from the core. This heat creates a cycle where hot material rises towards the mantle's upper boundary, cools down, and then sinks back towards the core. This convection process is integral to plate tectonics, the movement of the Earth's lithospheric plates that form the surface. The convective forces in the mantle push and pull these plates, causing them to move, interact, and reshape the Earth's surface over millions of years. But there's more to this boundary than meets the eye. Seismic studies suggest that the core-mantle boundary is not a simple, smooth transition. Instead, it's a complex region with mysterious structures known as ultra-low velocity zones. These are areas where seismic waves slow down dramatically, hinting at variations in temperature, composition, or both. The core-mantle boundary, then, is not just a line on a diagram, it's a dynamic, complex, and crucial region of our planet. It's where heat from the core drives the engine of mantle convection, powering the surface processes that shape our world. The core-mantle boundary is a crucial transition zone that plays a key role in the Earth's dynamic processes. Imagine a place hotter than the surface of the sun. This isn't a scene from a science fiction novel, but rather, it's the reality of the Earth's core. Nestled beneath thousands of miles of rock and metal, the core is a fiery furnace with temperatures reaching up to 9,000 degrees Fahrenheit. That's hotter than the surface of our sun. This extreme heat plays a crucial role in driving the geological activity on Earth. It fuels the movement of tectonic plates, leading to earthquakes and volcanic eruptions. Additionally, it powers the convective currents in the Earth's outer core, which in turn generate our planet's magnetic field. This magnetic field is vital for life as we know it, as it shields us from harmful solar radiation. So, in an intriguing way, the intense heat at the Earth's core not only shapes our planet, but also protects life on its surface. The extreme heat at the Earth's core is a driving force behind many of the processes that shape our planet. At the center of the Earth, pressure reaches unimaginable levels. Imagine the weight of the entire planet, from its crust to the outer core, all pressing down on a single point. That's the kind of pressure we're talking about here, a pressure so immense that it keeps the inner core in a solid state despite its extreme temperature. It's like having a billion elephants standing on a postage stamp. This pressure, in concert with the intense heat, creates the unique conditions that define the Earth's inner core. Iron and nickel, substances we commonly see in a solid state on the surface, exist in a forced solid state here, despite temperatures that exceed the surface of the sun. It's a testament to the extraordinary power of pressure. The tremendous pressure at the Earth's core is what keeps its heart solid, despite being hotter than the sun's surface.